In Part 4 of Lecture 4, we will discuss processors and memory. A central processing unit, or CPU, is the brain of a computer. When we are working on smaller computers, we refer to it as a microprocessor. The microprocessor's job is to process instructions that comprise our programs. In any digital device, the microprocessor will be the most important component. It will usually be the most expensive component as well. The largest designer and manufacturer of microprocessors is the Intel Corporation, which supplies most of the microprocessors used in desktop and laptop computers. The original IBM PC contained the Intel 8088 microprocessor. It differed from the 8086 microprocessor by the number of pins it used to connect to the motherboard. Later PCs used 8086 processors, and as time passed, the 8086 processor was replaced by later members of this processor family, including the 8286, 8386, and 8486. Members of the family after this carry the Pentium name. After the Pentium processor came the Pentium Pro, Pentium 2, Pentium 3, and Pentium 4. More recent additions to the x86 family include the Core processors, whose most recent member is the i7. The processors in current desktop and laptop computers are x86 compatible. Tablets and smartphones don't typically use Intel processors. Most of them use ARM microprocessors, which were designed by ARM Holdings, a British company founded by Acorn Computers, Apple, and VLSI Technology. One of the key characteristics of ARM processors is that they are energy efficient. This is important for battery-powered devices because no one ever considers the device's battery to have a sufficient power supply. The less electricity that a device uses, the longer its charge can last. ARM's processors appear in a large variety of devices, including Microsoft's Surface tablet, iPads, iPhones, and Samsung's line of Galaxy phones. Finding the best processor for you depends on your budget and what kind of applications that you will be using on your device. If you happen to know the brand and model of the digital device, you can usually find the specifications of the processor it contains online. The performance that we get from a microprocessor depends on several things, including the clock speed, the number of cores, and the cache. Let's look at each of these. Every processor needs a clock, which provides pulses at regular intervals. The clock speed tells us how many of these pulses occur over a time interval, which is usually 1 second. 3.4 gigahertz is a common clock speed in 2018, and it tells us that there are 3,400,000,000 pulses per second. Each of these pulses is used to coordinate the steps that need to be carried out to execute an instruction. It can take a handful of pulses or several hundred pulses to execute an instruction. But clock speed is a critical part of determining performance, even though it is only one of several factors. When the first PC came out in 1981, there was only one processing unit doing only one instruction at a time. That is no longer the situation. Many processors, including Intel's Core processors, the one commonly used now in PCs, have multiple processing units in one microprocessor. That's why they are called dual-core or quad-core or multi-core. Each of these can work independently of the others, allowing the computer to do more than one thing at a time. Traditionally, processors executed one instruction at a time. This is what we mean by serial processing. We are processing instructions in a series. Serial processing meant that we could not start executing the next instruction until we finished the previous one. If it took 5 clock pulses to carry out each instruction, it would take 25 clock pulses to carry out 5 instructions. But if we have the necessary hardware to allow it, we can fetch the second instruction while we decode the first, and then we could fetch the third while we decode the second and perform the first instruction. We can fetch the fourth while we decode the third, perform the second, and save the results of the first. This kind of assembly line processing speeds everything up. Those same 5 instructions, which take 5 clock pulses each, now only need 8 clock pulses, as opposed to the 25 it needs in purely serial processing. The drawing you see illustrates how a set of instructions is processed using serial processing, pipelining, and parallel processing. As we move from serial to pipeline to parallel, we can see how the performance improves, but it requires some extra complexity to the design of our processor. There are a few other factors that affect performance. While we consider memory to be close to the processor on the motherboard, from the computer's perspective, they really aren't very close. Most modern computers have special memory known as cache, either built into the processor or right next to the processor. The idea behind it is actually rather simple. We can assume that there is a greater probability that the next instruction to be executed or the next piece of data to be used may have been used very recently, so we save it together with its address in the cache. Every time the computer seeks an instruction or data, we check the cache first. We can search all of cache at once to seek if we have the contents of a particular memory location. If we do, we don't need to wait for it to come from memory. If it's not there, we haven't lost very much. Processors with cache perform far better than those without. The more bits that a processor can process at once, the higher the values that can be stored in memory as a unit, and the larger the maximum memory address can be. As a result, processors with a larger word size, the number of bits that the processor can manipulate at once, can work with more memory. Lastly, someone discovered many years ago that about 20% of a computer's instruction set handled 90% of the work. It begs the question of whether you really need the others. This led to simple designs with smaller, simpler instruction sets. These computers are called RISC, Reduced Instruction Set computers. And yes, they work significantly faster than older CISC design. CISC stands for Complex Instruction Set Computer. RAM, or Random Access Memory, is where data and instructions are held while the computer is working. It is also used to store the part of the operating system that is most frequently used. Adding extra RAM to a computer makes it more expensive, but it also helps the computer work faster, and it allows more programs to be active at once. RAM uses small electronic components known as capacitors to store the bits of our data and instructions. That makes RAM volatile, meaning that when the power is turned off, whatever is stored in RAM is lost. The reason for the name is that it can read or write at any address in memory, even if it is seemingly picked at random. Computers have another form of memory called ROM, read-only memory. It may seem that it can't be very helpful since we can read it but not write it. But the important thing is that ROM is non-volatile. We need a certain amount of memory like this. It is typically housed on the system board and contains instructions that the computer uses to check its components, load in the operating system, and start running programs. There are several reasons why you might want to change the contents of ROM. A power surge can corrupt the contents of ROM. Flashing the ROM to restore its original contents may correct the problem, otherwise you might need to replace the ROM chips. We may wish to make changes that might, for example, increase the programs that we can download. This isn't always advisable. It can cause more problems than it solves, or void the warranty on the computer. There may be data on the ROM that might indicate the presence of malware on the computer. Occasionally, there will be upgrades available for download that can be rewritten on ROM to improve computer performance or fix bugs.